Diffraction of light exposes the wave nature of light. Let's take a look at Fraunhofer diffraction pattern associated with a single slit. Here we have a helium neon laser with wavelength 633 nanometers, a set of narrow slits. The width of each slit is less than 1 millimeter. We have a cardboard with a circular aperture. The diameter of the circular aperture is greater than 2 centimeters. And we have a screen to observe the light. Now, let's start our experiment. I will place the cardboard parallel to the screen and in front of the laser box so that the laser beam passes through the circular aperture. What do you observe on the screen? We observe a bright spot of light having a diameter almost equals to that of the laser beam. As expected, light travels in straight lines. Now, let me replace the cardboard by a thin or a narrow slit. Observe. Okay, now what do we observe on the screen? We observe that light is deviated from its original path without being reflected or refracted. This phenomenon is called diffraction of light. Let's describe the diffraction pattern. We have alternate bright and dark spots or fringes on both sides of a central bright spot, which is called the central bright fringe. The central bright fringe is twice as broad as other bright fringes, and it is the most intense. Also, the fringes are aligned in the horizontal direction, but our slit is vertical. Then the fringes are aligned in a direction orthogonal to that of the slit. Now, what happens if I replace the slit by another one having a smaller width? Observe. The fringes become wider. Let's replace it by another one of a smaller width. The fringes also become wider. Another one of a smaller width. So, what do we conclude? We conclude that as the width of the slit decreases, the fringes become wider.